You know, you might as well. So, you know, we used to get really good postdocs and students, but from
challenging
European countries, and you know, now hardly any.
And come to me. So thank you very much.
Why not go to Germany or you know, France or you know, somewhere where it's
benefited a little bit from
you might as well.
Good. So pretty soon we're going to start. And make sure I think you guys see the presentation and have it ready so we can see it. And some panelists that we're coming. Try to follow my timer, which is of course the iPhone, which we cannot live without. Right. Okay. So let me start. So thank you everybody to come to the online spin phenomena into the SPICE and SPIN+X seminars. As you know, this is organized by myself, Chiral Interaction, running Spin Phenomena Interdisciplinary Center SPICE, in collaboration with Libor Schmeichel, Angela Wittmann, and Karina Bertossetti, that help us as scientific advisors, and in collaboration with the Collaborative Research Center SPIN+X, led by Martina Schliemann, Burkhard Hillebrands in Kaiserslautern, and Matthias Glow in Mainz. This is Zoom webinar, so you will see the speaker or the person speaking, and then you can write your Q&A in the questions, but also have, you know, can raise your hand and sometimes even write in the chat, and then I will moderate it afterwards and give you the floor to come into the panel to ask directly the speaker. Today's speaker is very well known in our field, Chris Marrows. He's a professor at matter physics experimental and in Leeds in the UK. Formerly part of the European Union, and now he got his BS from Leeds and a PhD as well from Leeds, and then has done most of his career there. He works, of course, in many aspects of magnetism, but particularly is very well known for his work on Skirmion physics and spin torques in magnetic nanostructures and artificial systems. And we're looking forward to his talk. So I'm going to stop sharing and ask you please to go ahead and share your slides.
Okay, so thanks, Chiral, for the introduction, and let me try and see if this is working. Yeah, okay. So,
yeah, it's working well. Yeah.
I do that and then start the slideshow like that.
Perfect.
And can you see my pointer?
Yes, we can.
Yeah, brilliant. Okay. Yeah. So yeah, thanks, Chiral, for the introduction and for the chance to present our work here in this series of seminars. So as you said, I'm going to talk today about our work on Skirmions, and in particular in Skirmions in magnetic multilayers. So you can see here a photo of the Leeds campus when, well, actually it's pretty sunny today, but there's not green leaves on the trees. I'd like to start really by acknowledging all the people who did the work that you're going to see, and quite a lot of what you're going to see was done by Katerina Zeisler when she was a postdoc in Leeds, and in collaboration particularly with Simone Finizio at the Powell Scherrer Institute. And this was when we were members. There was a European FET program called Magic Sky that we were part of and collaborated within. But lots of other people have helped us along the way with various things. I mean, all of the people at Powell Scherrer were helping us with synchrotron imaging, X-ray imaging, some Lorentz microscopy here, some modeling, blue ion light scattering, and then lots of people in Leeds contributed to making the samples, analyzing the data, helping out with beam times, that kind of thing. So let's begin at the beginning. So what are magnetic skirmions and what are chiral magnetic skirmions? So a skirmion is a kind of a twist in the magnetization of a magnetic material. And there are some pictures here that you will see in many Skirmion talks. So here, here's a sort of schematic representation of one. So we think of it as a sort of 2D object, but really it's in a 3D material. So it can have some depth. And if it's a thick material, it will be like a string. But if you have a very thin film, then it will just be this sort of disc-shaped object. And so the magnetization here is pointing down in the center. It's pointing up all around the edge. And what that means is we can embed this thing in a uniformly magnetized background. And the important thing about it, or one of the important things about it, is the fact that if you look within this thing, somewhere within it, you can find a spin pointing in every direction in space from up to down. And we can sort of think about that by going from this real space representation to kind of a spin space like this. So if we have a sphere, then we sort of completely cover that sphere with all of the spins that are found in our skirmion. And this is to do with one of the first important properties, which is that this thing has a special topology. It has a topology that is different from the uniform magnetic state. And if you're mathematically minded, then you would think of this in terms of winding numbers, and there's a formula here that lets you calculate the winding number. And so for this object, this number S would come out to be 1. Well, actually, I think -1 in this case, whereas a uniform state would be 0. So we have this thing with a special topology. And it also has a sort of particle-like properties. Once you've created this thing, they're often fairly rigid, and you can move them around. They can crystallize, like you see this example here, a Lorentz micrograph of some skirmions in this slightly exotic iron cobalt alloy here at low temperatures. And then if we think about spintronics, then the magnetic materials that contain these can often be metals, or at least can conduct a current. And again, this is one of the very popular images that you'll see in lots of Skirmion talks. If we sort of send an electron through this thing, and the spin tracks the local magnetization, then it will kind of go all the way around and come out again, pointing up, having gone in pointing up, but it's acquired some sort of phase on the way. So this is Mike Berry. We can say this thing accumulated Berry phase, and if you're happy with Berry phases, that's good. If you're a bit more simple-minded like me, then you can say, well, all this curvature stuff is a bit tricky, but I know what an Aharonov-Bohm effect is, so I know I get a phase from if I expose my electrons to some magnetic flux. So I'll pretend that's happened. And that's quite a useful thing to do with these skirmions, because it turns out every skirmion gives you, phi naught of this fictitious magnetic flux. And that magnetic field is fictitious, but the Lorentz force is real. The electrons really are deflected to the side like this, and you can measure that as a Hall signal. And you can even, there's even electrodynamics where, well, if we move the skirmions around, we can generate electric fields as well. I just want to dwell for a moment on this idea about topology, because it is sort of quite important. A few years ago, there was a Nobel Prize for topology in physics. Everybody thought that gravitational waves were going to win that year, but they didn't. And then there's a member of the Nobel Committee whose job it was to explain to all the journalists who'd written up their piece about gravitational waves what this topology stuff was. And he produced this bag of stuff from the bakery, because really topology is kind of just, in some sense, it's just counting, right? It's to do with properties that remain under like kind of smooth deformation. And one of the things that that you can't get rid of like that is a hole in an object. So here we've got in this case, a piece of bread that, well, throughout the UK it has many different names. I'd call it a bread roll. And it hasn't got any holes in it. So we'll call that 0. It's just a very simple object that's just a lump of something. But if we have a ring-like object, like this bagel, that's got a hole through the middle, and so now we can say, well, that's 1. And then it turns out there's a special kind of Swedish pretzel that looks like this that has 2 holes in it. So we can call that 2. And there are more complicated pretzels that have 3 and so on. So the crucial thing here is you can't have half a hole in something, right? If I can tear a hole through the middle of this and get something with the same topology as the bagel, but I can't have half a hole. And so you have to do something quite violent. It's not just a smooth change. And there's no sort of halfway stage. You've got discrete jumps between 0, 1, 2. And so if we're creating Skirmions, then again, we've got to do something quite violent where the magnetization has to be kind of ripped apart and put together again to create or destroy them, and that helps make them stable. And you've either got one or you haven't. You can't sort of have sort of half a one. And that makes them attractive from the point of view of data storage. If we want to store data, then it's quite nice to have something that's a bit robust against at least sort of small perturbations. So again, as an example, we could sort of think of this Möbius strip. So here we've got a simple loop of paper with 0 twists in it. And here we've got a Möbius strip, which has got 1 twist in it. And this is a winding number, like the Skirmion winding number. And so, well, I could say, well, now I can store a bit of digital data in this loop. If I call this a 0 and this a 1, and by looking at the twist, and then I can, once I've done that, I can treat this quite roughly. I can scrunch it up into a ball, throw it in a bag with some others, and get it out. And if you get it out again, as long as you can still see whether there's a twist or not, you can recover your data in spite of all those other things that have happened along the way. And so this is why it's sort of attractive to think of using Skirmions in this way. So a new kind of a twist, if you'll pardon the pun, on magnetism that came along with this was this idea of Dzierzhalinski-Maria interaction. This is quite a mouthful, so we tend to call it DMI. And it's a chiral interaction. So normally in magnetism, we think of Heisenberg exchange, and we have 2 spins and we have the dot product between them. That gives us collinear states like ferromagnetism. This DMI, it was proposed by Dzierzhalinski and Maria several decades ago, and was used in sort of various more sort of exotic corners of magnetism. But it turned out to be really important in stabilizing these Skirmions, and now it's something that's very found its place in magnetism and is very widely studied. So it requires 2 things. You need a spin-orbit coupling, and you need an inversion asymmetry in your material. And the first Skirmion materials, like that iron cobalt silicon that we saw before, this was done at the level of the lattice. So here's a unit cell of this B20 lattice that those materials have. And you can see it sort of has a rock salt structure, but it's been twisted. Every atom's been displaced a little bit from the corners of this cube. So you have a cubic unit cell, but the basis inside the unit cell has a twist, has a handedness, and it lacks inversion asymmetry. And that gives rise to this DMI. Or in the kind of materials we're going to be looking at now, we look at interfaces. So again, we have an inversion asymmetry because there's a different material above you and below you if you're positioned at the interface. And this in fact gives rise to this interaction between 2 neighboring magnetic moments that has this cross product form. So it's chiral, it has a handedness, and if this were all you have, you would have these moments would like to lie perpendicular to one another. Usually what happens in practice is they sort of twist away a little bit from a parallel or anti-parallel state. So you have a ferromagnet, you add a bit of DMI and everything kind of twists a bit. And there's sort of two ways that this can happen. So you can either get a helical twist or a cycloidal twist. In these interfaces, you generally get this cycloidal one. So these look like Nael domain walls. These look like block domain walls. And if you create a Skirmion by kind of twisting one of these domain walls into a loop, then you can get these block or Nael Skirmions. So for pretty much the rest of the talk, we're going to be looking at these Nael type ones. Obviously, lots of groups, including those in Mainz, have looked at this as well as us. So at the round of the time where, so these are sort of all early examples, at the round of the time when people were thinking of looking for Skirmions in these kind of multi-layer systems, lots of people found them. So you can see here various different material systems and a micrograph showing these little blobs of contrast, which are the Skirmions. And if you look at these multi-layers, they're all sort of similar. So here we've just got a tri-layer in this box on the left. So you have a magnetic layer, which is very thin, so that its properties are dominated by the interfaces. It's often cobalt or something that's got cobalt in it. And then you have above and below at least one heavy metal and maybe two. And they give rise to the DMI properties that are needed to create the Skirmions. So you can have this tri-layer where you have a ferromagnet with something above and below it, or you can take a whole stack of those tri-layers and pile them up into a multi-layer, and there are examples of that on the right here. And you can see these Skirmions are, they can be pretty small. These are the biggest on a sort of micron scale, but more often you're down in the hundreds or even tens of nanometer range. And I think the smallest that's been seen to date is a little more than 10 nanometers. At least at room temperature, you can do fancy things at very low temperatures. And as I said, so this is a handful of the earliest papers, and there are a huge number more since then. So it's become a very big, very popular topic in a very big literature. So let's take a look then at the sort of materials that we were making and have been studying sort of since that time. So it's if we have a look here, there's a sort of schematic of the multi-layer, and there's a cross-sectional TEM image of what's inside it. So we have our ferromagnetic layers. In the simplest case, they're made of cobalt. They're slightly less than nanometer thick. These lines in the image that you can see are the planes of atoms within the multi-layer. They're the lattice fringes. So you can see there's sort of 3 or 4 planes of atoms thick. And so their properties are totally dominated by the interfaces. So they're magnetized out of plane because you get an anisotropy of these interfaces. That's what these polar Kerr loops show us. But they also, have quite a strong DMI because of these dissimilar metals, platinum and iridium, above and below them. So these are some of the very first images that were taken actually by Javier Palacio at Brookhaven Labs in the Lorentz microscope that they have there. And we've colored them in with some false color. So the sort of bright and dark bits around the edges, that's the Lorentz contrast. And then we've colored the rest in either blue or red to signify something that's either magnetized, towards you or away from you. So we get these sort of fairly typical dendritic domain structures, but you can see here and there, like these little objects, like there's one here, there's one here, maybe one here, that are sort of little detached, discrete things. And if we kind of zoom in on one of those, here's one. It's about 150 nanometers across, and that's that's a little skirmion by itself in this multi-layer system. Now, most of the rest of the results that I'm going to show you, we used scanning transmission X-ray microscopy at the Swiss light source, which is, so there's a microscope about here in this storage ring in Willigen. And the way it works is that, well, here's a picture. So you know, your sample goes in here, you shine X-rays through it. It has to be transparent to X-rays, so we make our samples on these very thin membranes of silicon nitride that are maybe 100 or 200 nanometers thick. And there's a detector at the back that measures how much light you're shining through. You focus, you bring your beam to a focus at a point in your sample, and then you sort of scan the sample around. And as you scan it around, you will transmit or block more or less of the beam, and you can sort of build up an image of what your sample is like. And the way we get magnetic contrast is using this effect called X-ray magnetic circular dichroism. And in that effect, your X-ray photon comes in, and it can promote an electron from these 2p levels up to the Fermi level. And because of the quantum selection rules, the circular polarization of this light depends whether you pick out spin up or spin down electrons. And then because at the Fermi level, there are more states available for one spin than for the other, it's easier to promote one or other spin. In this case, it would be spin up. And so what that means is that for the handedness of the light that picks out spin up, you'll get stronger absorption, and that means less light falls on your detector. So what's important is the relationship between the helicity of the photon and the component of the magnetization along the beam direction, which is the film normal in our case. And if you scan the energy, here's an example for nickel. You pick out the L3 and L2 X-ray edges, which correspond to these 2p levels, and you can see there's a difference between positive and negative circular light, the level of absorption that you get. So to make a magnetic image, then you would go to, say, in this nickel L3 edge here. This is a disk of permalloy. This is a nice example that Simone made to show us how it worked. So you take an image, and here it is. And then you flip the helicity of your light, and you take another image, and here it is. And at this point, you're thinking, well, you know, I can't see much there. But if we take, you know, the difference over the sum of these two images, then these rings appear. And that's sort of these ring-shaped magnetic domains inside this permalloy disk, which is mostly made of nickel. So what you can do is image the Z component of your magnetization, and that's very useful for seeing these skirmions. So here's again one of our first examples. There's a 1 micron disk of platinum, cobalt, iridium multilayer with 10 repeats. And you can see most of it's magnetized one way, but there's these two little patches that are, you know, maybe a couple of 100 nanometers across or a bit less. And they're magnetized the other way. So there are a couple of skirmions that are existing inside this disk. This one's pretty circular. This one's actually a little bit slightly deformed. So we're looking at the component of the magnetization that's in or out of the plane. Then, you know, around here, around the edge of this, we'll have these in-plane moments that give us the male skirmion. So I touched a little bit earlier on the fact that people were sort of attracted to these skirmions because they seem like a nice way of storing data, because they're topologically stable. They can be very small, so you could have high density. And it turns out they can be quite easy to move around using spin torques. And lots of people will talk about racetracks, where we have, we can encode a stream of data as a pattern of skirmions along the wire that we can move around with spin torques. That may or may not be useful, but you can kind of go on from that and say, well, I could make networks of these tracks, and then skirmions can meet at these junctions and perform some sort of logical operations. So you could imagine maybe some sort of system that could compute something in a Boolean way, or instead of that, we could think, well, let's do something neuromorphic or probabilistic. So this was a proposal which has actually been realized now in Matthias's lab. So we have a sort of chamber where skirmions can diffuse around, and they can help sort of generate probabilistic signals for probabilistic computing. But to do whatever you want to do in the end, there's some basic elements of that. So if we go back to the racetrack, we can sort of see what they are. You've got to be able to write data, so you need to be able to nucleate skirmions. You need to be able to move that data around, so you've got to sort of propagate them from one place to another, and you need to read your data back, so you need some sort of read element that can detect the skirmions. And in a spintronic device, you'd like to be able to do all of these things electrically. And so in the next bit of the talk, I'll show you that we did manage to do all of those things. So we'll start with nucleation. Okay. So this is our nucleator device. And so that, again, there's some false color here to help you understand it. The magnetic wire is this rectangle in the middle. So that's a 2 micron wide wire, and it's made of the same kind of multilayer that we've seen already. And it's got copper electrical contacts at either end. And one of those is shaped into this sort of finger that you can see here. And there's a radius of curvature at the tip that's about 250 nanometers. So if we send a pulse of current along this wire and inject it from this finger, then there's going to be a sort of very high current density at the tip of the finger that spreads out into the wire. And then on top of that, electrically insulated from the wire, we've got this, what we call an omega coil. So it's a sort of half turn of copper that we can put a current through, and we can generate some vertical magnetic field in the center that can basically just remagnetize the center of the device. So, well, here we can see it working down here. So if we look at these 3 images, it's now on its side. So here's the tip of the finger, and here's part of the coil. Here it is in a uniformly magnetized state. And then we inject what we call a set pulse through the finger. And we've now got this patch of dark contrast. So that's a skirmion that was created by the current pulse. Then we put a so-called reset pulse through our coil, and it gives us this uniformly magnetized state back. And then we can do that over and over again to look at different conditions, or look at the dynamics. So basically, this is what we see. So here we've got lots of little micrographs with the finger always coming in from the left-hand side. This is how long the current pulse was that we injected. And this is the current density, which we've calculated once it's spread out into the wire. So, down here, the pulse is either too short or too weak. Nothing happens. And up here, the pulse is either too long or too strong. And we've overheated our wire and filled it with some sort of complicated domain pattern. But there's this sort of band across the middle where we get a single patch of dark contrast, a single skirmion appearing, at the tip of the finger. And I should say this is all done at 0 field. There's no applied magnetic field here, and it's especially in the center of this band, it's super reproducible. We called it deterministic. You really can just press a button and send in the current pulse, and a single skirmion will appear, very, very reliably. It's just one of them, and it's always one. And so we can build up this sort of phase diagram where the single skirmion states are these light blue dots, across the middle here, where we see something like this. And it turns out that we have a bit of control over the size as well. If we calculate, the charge contained in the current pulse, then, for a given duration of pulse, we get these sort of straight lines of the skirmion area. So we've sort of got like a balloon that we're inflating up to a certain point, and then the current switches off and it stops. And then, we studied that at high speed as well, because they like to do magnetization dynamics on that microscope. So there's little movies here, but maybe if you look at these snapshots, you can see 0 is the start of the pulse, and this patch of dark contrast kind of grows. And this row is as annihilating it again with the field. So this is kind of the thing that's most interesting to me. And this graph shows you what's happening there as a time series. So the red curve is the current pulse from the oscilloscope. So it's nominally 5 nanoseconds long. You can see that there's rising and falling edges that are, there's maybe sort of half a nanosecond of spreading there. But the skirmion appears and starts to grow immediately, and grows more or less until the pulse switches off. So the fact that there's no incubation time makes us think this isn't a thermal process. This is something that's driven by spin orbit torques from the current pulse. Okay, so we can create individual skirmions, sort of at will. The next step in our racetrack sort of frame of thinking is propagating skirmions around. So here we've got kind of a similar structure, actually. This experiment is actually older than the nucleation one. So this is a 2-micron wire, exactly the same, but it's just got flat contacts at each end. There's no nucleation finger. But what we found we could do was, if we put in a kind of moderately strong current pulse, we could fill it up with skirmions. So that's what all these little patches of bright contrast are that appeared in this wire. And then we could apply these sort of somewhat weaker pulses. Here they're 9 nanoseconds long, and they're about half a teraround per meter squared. And we would take an image like this, and then we'd apply 2 of these pulses. And then we'd take another image and see what had happened. And quite a few of these skirmions would have moved a little bit. And so as you repeatedly apply pulses, you can track out their motion. And that's what these sequences of colored dots are. Each one is a single skirmion that's kind of moved down the wire. So this is at 0 field. If we did this, repeated the same experiment at sort of more and more negative fields. Here, a negative field is one that is opposed to the magnetization in the center of the skirmion. So it's the field is sort of trying to compress this skirmion. If you think of it like a bubble, the field is trying to compress the bubble a little bit, make it smaller. So you can see a couple of things. First is that these skirmions sort of all move down the wire, or well, many of them move down the wire in the direction of the conventional current flow. So electrons are flowing from bottom to top, conventional currents flowing from top to bottom. That makes us believe that it's spin orbit torques which are causing the motion. And you can also see that as well as moving down the wire, they all sort of tend to drift to one side, in this case, the right-hand side, more often than not. And you can also see that it's not very reproducible. All of these skirmions follow sort of different tracks. Some of them move much further than others. And so, you know, it's what's going on is kind of quite disordered, and we're going to have to average over quite a lot of measurements to understand what's going on. I just want to briefly mention this idea of this field. So the idea was there were, at the time there were these models that said that the angle that the Skirmions move at with respect to the current should depend on their diameter. So we wanted to see if that was true. And so to adjust their diameter, as I said, you can do that with the magnetic field. We apply this negative field, we should squeeze these Skirmions down. And that's what we sort of saw up to a point. And that point's about here, where some of the smaller Skirmions get annihilated. And then the average size jumps up again a bit because you've only got, you know, the bigger ones left. But it, you know, it does work that you can kind of squeeze them and make them smaller. So let's have a look at what we found. So this motion of the Skirmions at an angle is called the Skirmion Hall effect. And you can make it, it's very timely. I guess that the World Cup is on at the moment. Although there's not many teams left now. England are no longer there, unfortunately. Neither are Germany. As we all know, very skillful players can put spin on a ball and it will curve as it moves through the air. And that's because of the so-called Magnus force to do with this, this rotation and the different pressures on either side of the ball. And this is important in lots of ball games, tennis as well. You know, spin is absolutely crucial, for instance, or snooker, pool, billiards, all kinds of ball games. Our Skirmions behave in a similar way. Because they have this chiral structure, there's what's called a gyrotropic motion, which means that if you push them, you generate a force in the direction that you're pushing, but you also generate a force that is at right angles to that, a bit like this Magnus force. And then the upshot of all of that is that the Skirmion moves at some angle to the drive in, you know, the flow of a current, for instance, and that angle is known as the Skirmion Hall angle. So that's exactly what we saw a couple of slides ago in our wires. The Skirmions are not moving straight down the wire, they're moving at some angle and drifting to the side. So here, if we take all of our data for every Skirmion at every size, measured at every field, and just throw it onto this plot, then we can measure the Skirmion Hall angle and plot it as a function of the Skirmion diameter. And remember, the theory told us these things should be related. We don't see much relationship in this data set. It's not obvious that the angle's any different for the larger or smaller Skirmions. So we've got ones here that are 700 or 800 nanometers across, a few here that are 100 or less, mostly in the middle, like 300, 400, 500. So the average angle is around 9 degrees. This cloud of data points is slightly above 0, but you know, there's no obvious dependence on diameter. What we did find is if we plot against the velocity of the motion. So here again, we've got the Skirmion Hall angle, and we've got how fast that particular Skirmion was moving. And you can see mostly they're sort of 5 to 10 meters per second, something like that. There are a few that are moving much faster, and quite a few that were moving a lot slower. And what you can see is, again, there's no particular dependence of the angle on the velocity. It's still an average of about 9 degrees. But what you can see is there's a big change in the spread. So over here, the angle tends to be not too far from that 9 degrees, whereas here, at these very low speeds, the angle can basically be almost anything. It goes from kind of -90 to -90. And the way we sort of understood that is, well, some of these Skirmions are quite free to move. So when you push them, they'll go quite fast. And they'll move with a Hall angle that's sort of their intrinsic value. And in fact, this, this sort of 9 degrees more or less fits what you'd expect for these kinds of Skirmions. Some of the Skirmions aren't very easy at all to move. So if you give them a push, they don't go very far or very fast, and they tend to move in a direction that's probably down some gradient in the energy landscape they're living in, rather than anything much to do with the driving force. So we can sort of see that energy landscape if we just take all of our images and add them together. So that's what we've done on the left here. And what you can see is that this is not uniformly grey at all. There are some bright patches and streaks separated by dark regions. And so these bright areas are where we are very likely to have seen a Skirmion. And they will sort of move down. There are sort of roadways that they follow through the material. This image here is if we take sort of differences and add them all together. So here the bright regions are where you're likely to find Skirmion motion if you push them. And again, you can kind of see these tracks. So there's a sort of material science thing to work on here, which is to get if you can get very beautiful material that's very flat, then the Skirmions can move around more easily. And in fact, this sort of diffusion in these flat landscapes has been seen in mines. Other Skirmions can matter. So as well as the landscape, we do see some evidence for interactions. Sometimes Skirmions just disappear when you push them if they're in a pin site. Sometimes they fuse together, and sometimes they deflect from one another. I'd like to talk now about actually an even earlier experiment, which was the Skirmion detection. How do we read these things back? And so I want to go back now to the sort of berry phase idea of how that could generate a Hall signal. So I told you that accumulating berry phase can lead to Lorentz deflections of the electrons. This is called the topological Hall effect. And it was first found in the same materials that Skirmions were first found in, these B20 materials. So this is a single crystal of manganese silicon, and there's a certain range of fields where it has a Skirmion phase. And in that phase, we can see this sort of excursion in the Hall resistivity. This was a thin film of iron germanium that we made. And again, we get this sort of, in the Skirmion phase, we get this sort of excursion in Hall signal. And this was the Takura group in Ricken. They made a little nanoscale Hall bar out of iron germanium. And they sort of see these traces with jumps and steps in. And they sort of identified those as being the motion of individual Skirmions moving around within the sort of little Hall cross that they were measuring. So yeah, you measure a Hall signal, and that contains ordinary and anomalous, as well as this topological part. We can write down the topological part as coming from this effective field that's coming from the berry phases. We can convert that into a Hall resistivity with the ordinary Hall coefficient and a spin polarization that goes in front. But to pick this out from the measured signal, you have to get rid of these two other components. Now, at around the time we were getting interested in this, of course, we were not alone. Other people were sort of looking at thin films. This is a thin film of manganese silicon. And again, there's this, you can see this sort of Hall signal when you subtract out the other bits where you can pick out this Skirmion phase. Or people were just starting to look at these multi-layer interfacial DMI systems. And there were a couple of publications that came out whilst we were doing our experiments. So this one is from a group, quite a large group that was led by Christos Panagopoulos in Singapore. And they did MFM imaging, and they also extracted, they measured the Hall signal, subtracted off all the other bits, and they see these excursions, around the fields where they're seeing Skirmions, and they got a few tens of nano-ohm centimeters of Hall signal here. This experiment was done by Vincent Cross's group in Palaiseau, and they also did MFM. They would count how many Skirmions they had in their Hall cross, and they would measure the Hall signal. And what they found was, the more Skirmions, the more Hall signal you had, more or less straight line. But they said they could account for all of this signal, about 3 nano-ohm centimeters for every Skirmion, just from the anomalous Hall effect from the reverse magnetization. And there's no topological part, whereas here, everything else has been subtracted out. So this, this is topological or something else you haven't thought of. So there's a sort of a discrepancy here between these two experiments as to what you're really measuring when you get these signals. So the way we went about this was, again, we were in the microscope in Switzerland. We have our disk of multilayer. It's platinum, cobalt, iridium again. We've got Hall contacts, and we can look at it in the microscope, and we can measure in the microscope. So every time we make a Hall measurement, we can image the spin texture that's given rise to that signal. So this was actually before a microscope upgrade. So you're now used to looking at good images, and these are a little bit rougher. But here we've got our disk, 1 micron disk, saturated, up, saturated down, bright and dark. We can get kind of domain patterns inside it. And, here's a single Skirmion, a little patch of bright contrast in a dark background. So we got our Skirmion in the disk, and again, we applied a field to squeeze it down. So as we go to 10, 16, 45, 50, it's shrinking. At 75, it's gone. We've got a uniform disk, and we can track the Hall signal, which goes down as we squeeze it down. These red lines correspond to the fields with the images. We can measure the diameter, and we can measure the magnetization in the disk, sort of based on the image. And these are various kind of sweeps up and down before we annihilate the thing. So it's, it's sort of somewhat reproducible. And then to try and extract something from all of that data, again, we plotted the magnetization in the disk determined from the image, which saturates here at +1, with the normalized Hall signal, which saturates here at -1. And you can throw all of your points into this plot, and you get this kind of cloud. But if you rebin them, then you get this quite decent straight line. Now, if all you had was an anomalous Hall effect, which would mean your Hall signal was just proportional to, how much magnetization you'd reversed, you'd be on this gray line here. And we're on a line that's parallel to that, but offset a bit. So this change, the size of our Skirmion is changing. That moves us up and down the line, and the slope fits with the anomalous Hall signal. But there's a sort of size independent part of the signal as well. When the Skirmion disappears, we get this jump, and that's associated with this change in topology of this winding number from 1 to 0. So it's sort of tempting to call that a topological Hall effect. Well, in the end, we had to measure quite a lot of different disks under quite a lot of different conditions to sort of really see what was happening. So here's an example where we've got 2. I mean, this is definitely a Skirmion. This is sort of stretched out to be a domain, but there's 2 objects, and you can blow them up into domains. This is -2 because the contrast's the other way around. Here there are 3 objects. This one's probably touching the edge, maybe this one too. They're certainly touching the edge when you blow them up into domains, but you can still sort of count 3 objects inside the disk. So let's take all our data, put it on this plot. The green data are the ones that we saw before, but now we've also got red, blue, and purple for different winding numbers. And we're sort of comparing to this line, this grey dashed line for anomalous Hall effect only. So we can subtract that off. And then if we kind of look at the average level within each of these groups of points, you know, this is sort of what you get. So these red lines are the important ones. So we've got 0, 1, 2, 3, -2 of these Skirmion objects, and you get a reasonable sort of straight line fit through that tells you you're getting about 22 nano-ohm centimeters for every kind of Skirmion object you've got in your disk. Now, if you use that Berry phase theory and try and calculate what you'd expect, you would find that it was something about 1,000 times smaller. So there's it's not immediately obvious how to interpret these data. You know, maybe you can need to modify this theory somehow, or maybe you need a new theory. But certainly this is sort of consistent with what that Singaporean group found, and in fact they published another paper. This is in Nature Comms now. Actually, they found another this sort of signal of similar magnitude in a couple of other papers. So there's really something going on there. I think there's a bit of a challenge to theory here to sort of figure out what that is. In the last couple of minutes, just before I finish, I want to tell you a bit about what we're looking at the moment, which is Skirmions in synthetic antiferromagnets. So here we've got multilayers. This is a theory paper. You've got multilayers where, as well as the anisotropy and the DMI, you have another interfacial effect which couples the layers antiferromagnetically. So here's an example of a pair of Skirmions coupled together, but they're of opposite sign, opposite winding number. So although you've got a topological object, you've got a total winding number here of 0. And what that means is, well, the Skirmion Hall effect should go away, but there are also predictions that these Skirmions should be faster to move, can be smaller as well. So we thought this was a sort of interesting thing to look at. And then COVID happened. So we did some simulations. So you can make these things in Mumax quite easily. Here's some sort of reasonable numbers for all the micromagnetic parameters, and you find the right sort of things. You know, like if you make coupling strong, all of your Skirmions converge to the same size, and they behave in the field the way you think. What we did was kind of drive them with RF fields in our simulation. So here's an example. You know, there's 4 layers, no big surprise. You get 4 modes in the spectrum. But what is interesting is that, you know, sort of individual layers can be oscillating quite strongly, whereas the net effect may be, you know, quite weak sometimes. But sometimes the net effect is quite strong, you know, like, so maybe these first and second peaks, there's quite a bit to see. So this could be a way to detect Skirmions, because in these antiferromagnets, it's hard to see what's happening because there's no net magnetization. So a lot of the imaging techniques that you might try and use to see a Skirmion won't work. But you know, you could sort of excite your material at high frequency, and if you see a peak, then you know, you might know that Skirmions are there. And then we built an injector device as well. What we found is that quite often you get domains that span the width of the wire. So here's one of these finger things, and here we've got a domain wall in our synthetic antiferromagnet. And it's moving back and forth, and you know, we can, so pulses to the right, pulses to the left inside the Stixon. We can see that happening. Turns out these domain walls move reasonably fast. Actually, here's velocity against current density. So there's a region here in the middle where you get nothing. but it doesn't take a huge amount of current density to get up to sort of 30-40 meters per second. This curve probably continues quite a bit further, but we didn't have many devices at the time we did this measurement, so we stopped here because we didn't want to explode anything. But what you can, these are data points from conventional multi-layer domain wall motion. What you can see is you can get motion at the same speeds for substantially reduced current density if you go to the synthetic Antifarobacter structure. And you can even sometimes nucleate a single skirmion. There's a couple of examples here of a little patch of dark contrast. So these are synthetic antiferromagnetic skirmions that we've nucleated electrically. Right. So you can do a lot in these multi-layers, and you can do it all at room temperature. We've created single skirmions. We can move them around with currents. We can detect them electrically by means of their Hall signal, and you can decompose that into a size-dependent part, which is easy to understand, comes from the anomalous Hall effect. And then there's a size-independent part, which seems to require some theoretical innovation to really get to the bottom of what's going on. Maybe you need to revise this Berry phase theory, or maybe you need to come up with something new altogether. So yeah, thanks very much for listening, and I'm looking forward to some questions and discussion.
Thank you very much. Let's see applause from the audience. So I think we have now time for some questions. There's some written. Does it me allow to? I think Satish. I think I've given you the. Oh, let me see, I'm trying to allow him to. Oh, Satish is joining now. Can you unmute yourself and ask your question that you wrote on the? And of course, anybody, please raise your hands and I'll promote you to join. Satish, can you? I'm not sure. Maybe you cannot. Go ahead.
I can. I've managed to find in Zoom the Q&A, so I can see.
Let me read the question for you then. Oh, his mic is not working. He's actually saying that. So, a research scholar in India recently started experimentally work on magnetic Skirmions as silicon 100 is compatible with CMOS technology. I'm trying to enhance the transition between the iron germanium chiral thin films with induced strain from the buffer layer. Then I want to observe the helical of the Skirmion states using LTEM. As the sample thickness of LTEM samples should be around a few microns. Is it possible? That's a question now. The question comes. Yeah, is it possible to just to put in the context of what he was doing? Is it possible to study the samples prepared on a single-side polysilicon wafer using LTEM?
So yes, but not without doing some more work. So I mean, actually, even a few microns is too thick. I should say, actually, we're not a Lorentz microscopy group, but the groups that we work with quite a lot, I know the kinds of things that they do. So really, for Lorentz microscopy, you need something that's probably only 100 nanometers thick. But that is possible by, and in this case, I think the way that I would try is these groups, they very often prepare their specimens using a focused ion beam. So there are ways where you can do a sort of planar lift out, where you dig a pit under part of the film, make a lamella that's thin enough for Lorentz microscopy, and then lift it out and mount it on something. So yeah, it's possible, but you need some fancy specimen preparation in a focused ion beam to do it. But most Lorentz microscopy groups have that kind of technology, I think. Okay,
excellent. If of course, please raise your hand if you have a question. I don't see so far so many. Okay, there you go. Let me put Rundong. Can you maybe unmute yourself and ask your question?
Yes. Thank you, and thank you for the vivid presentation. And I'm concerning on the Skirmion size. Yes, you have mentioned that the length of your current pulse can determine the Skirmion size within your magnetic field. And I have little questions about, so how can this pulse size influence the Skirmion size, and any other factors of the substrate film system could have impact on the Skirmion size? Yeah, thanks.
Okay, so there's sort of two things to think about here. So if for a certain set of parameters like anisotropy, DMI, and so on, if you do a micromagnetic simulation, you'll find there's a sort of certain natural Skirmion size that corresponds, to the point where all those energies balance out. And in those simulations, you're normally dealing with a very perfect ideal material that's totally uniform. And so the Skirmion can easily relax to find that sort of natural size. What we found in our materials, because they're real materials with quite a bit of disordering, is that the Skirmion size can be sort of hysteretic, there's pinning, and you can have different metastable sizes under the same conditions depending on what you just did to your system. So this is an example of that. All of those images were taken at zero field after we'd applied the pulse, when everything is relaxed and stabilized, and we can see that we can stabilize Skirmions of different sizes. One of those sizes is probably the natural one. And so, but the sort of model we have in mind there is, as you're injecting your current pulse, you create this bit of reverse magnetization, and then you're sort of inflating it like a bubble. We were in a regime there when the pulse turns off, the thing just stops and fixes at the size that it had reached. When that inflation process ended. So that's what we sort of think is happening, and the pinning in the material keeps it like that, at that size. Now, obviously, if you're very good at sort of material science and synthesis, you can find ways to make even smoother layers that are even more uniform, even more homogeneous. You will find that there's some more relaxation is possible, and then it's those sort of just those intrinsic properties that will determine the size. So there's sort of two things to think about. There's those intrinsic micromagnetic parameters, plus all the extrinsic stuff that's coming from pinning and disorder in your material.
Yeah, thanks. I know what you mean. Thank you.
Yeah. Okay. Thanks.
Is there any other questions from the audience that you would like to ask Chris? Okay, Igor, hang on for a second. Let me promote you to panelist, so Igor will come. Takes a few seconds to join as a panelist. Yeah, Igor, can you unmute yourself and ask your question?
Yes. Excuse me.
Go ahead.
Okay. My question is the following. I didn't manage to catch what experiment can say something about inner structure of this inhomogeneous. The matter is that I'd like to understand what forces you to think that it's indeed some Skirmions or this inhomogeneous things have some other nature. It's possible also, right?
You mean that the texture in the magnetization?
Well,
or do you mean the material itself?
No. I mean just single spot. Yeah, which
okay.
Interpret like Skirmion. And I'm asking about some experiment which says something about inner structure of this
Right. Okay. Yeah. So yeah. So most of the images I showed, and like this one that's on that's on the slide at the moment here. Yeah, you're right. We're only seeing the Z component of the magnetization, but around the edge of this thing, there's got to be some rotation of the magnetization from up to down, which in this technique you can't see. You can only see this one component. So the kind of things we've done there are, so there are other X-ray microscopy techniques like PEAM, which we've done to look at the chirality of walls, where you can, and it comes down to, again, well, my light's coming in a certain direction, and I can put my sample in different places and pick out different components of the magnetization, and then you can sort of build up the whole spin texture if you have resolution enough. So we're very, on the basis of that, we're very confident that we have nail walls around these patches of contrast, and they really are skirmions. I mean, another technique that can tell you something about that is Lorentz microscopy. So also where those very first Lorentz images that I showed you, and we've done a little bit with other collaborators as well. Again, you sort of tilt your sample in different directions. So you're trying to sort of pick out different components of the magnetization, and you can build up an image of what the whole spin texture is like and what that internal structure is. So I kind of glossed over that a bit and said, here's a little patch of dark contrast, that's a skirmion, and just that ask you to believe me. But we have checked that that there really is a sort of internal. We have checked to be confident that these really are skirmions and have the right topology. And if you wanted to be very careful with those techniques, you could build up a full 3D structure of the whole internal structure of the skirmion. I mean, and probably plenty of other ways to do it as well.
Yeah, I think maybe some like scanning electron microscopy with polarization analysis, like SEMPA, can actually be used.
Yeah, I mean, all of the various sort of quantitative MFM methods, this nitrogen vacancy center imaging. Usually you're picking out one component of the magnetization, but if you measure again and again, picking out different components, then you can build up the full vector map of your magnetization texture.
Okay, well, question is actually arises because all these theoretical calculations usually are based on micromagnetic simulation, where there are quite strong assumptions are used. And when you make these experiments with lights, then different materials have different matrix elements of interaction with light, and correspondingly different rotation angle in this experiment with rotation of polarization plane. And this does not exist in this kind of simulations, right? Yeah. So
okay.
Yeah, well, question is, if you have different materials and different similar structure, probably one can say from other experiments what kind of difference in this matrix elements and so on, and to what extent this micromagnetic calculations indeed catch the picture. That's what I am.
Yeah. Okay. Yeah. I think I know what you mean.
Okay. Thank you.
Thanks.
Okay. So one thing that I wanted to comment on, ask you a little bit about, so this normal solar effect, which is actually in part of Igor why it's a little bit of understood that the topological contribution to the normal solar effect follows a little bit of the micromagnetics, which assumes this adiabatic motion of the electrons following the magnetization profile, which wouldn't happen if there were just bubbles in this case. So you mentioned that there's a size-independent component that is not proportional to how this skirmion is changing, right? Or the
yeah. So If I can get
And
back
then
into
in this case, in the analysis, did you identify that there was there's essentially there's a finite magnetization, the component of it, or?
Well, so maybe this is a good example to go. Well, if we go back even here, okay.
Yeah.
So what the situation here is, we've got a single Skirmion in our disk. And as we apply this field, we can squeeze it so it gets smaller, and then, you know, eventually it disappears.
Okay.
And, you know, so that's what's happening here. You know, as we measure the Hall signal as that process happens, we're squeezing this Skirmion so it's getting smaller and smaller.
Right.
And, you know, the magnetization is growing, it's approaching saturation because this little reverse region is getting smaller and smaller. So we see this gradual change in the Hall signal. And that's exactly what you would expect from the anomalous Hall effect. Because as you squeeze this thing, it gets smaller, there's less reverse magnetization. And
But
so
you're essentially assuming
so
that.
this, so yeah, so the slope of this line you can explain just through, you know, the anomalous Hall effect. But then at the end, when the Skirmion is annihilated, you get this jump. So that's the sort of size independent part. Yeah, there's this size dependent part as you move up and down the slope of this line, which is totally consistent with what you'd expect from the anomalous Hall signal. But there's this jump, which is, you know, is not. If all you had was an anomalous Hall effect, you just go up and down this gray line, which has got a slope of -1, which is just magnetization proportional to, sorry, Hall signal proportional to the Z component of magnetization. So the size independent part is this jump, which corresponds to this change in topology, and that's the bit that needs further explanation. So if you could just say, well, that's the topological bit because there's a change in topology.
No,
but it's not quantitatively consistent with the Berry phase theory.
Well, yeah, I will have to look at the numbers. I mean, essentially, you do have, as long as you do have is finite amount of Skirmions, and but if you're just sampling one Skirmion only through that sample that you're measuring in, then this, you know, the topological Hall effect should be proportional to the gradient that you've experienced, because that's the effective field, orbital effective field that you.
Well, yeah. So that is,
and that's a slope. Yeah,
that would be this graph here.
Yeah, exactly.
So here's the number of Skirmions, or the Skirmion winding number.
Yeah.
You know, 0, so, you know,
Exactly.
0, 1, 2, 3, or -2.
Exactly.
And then this size independent bit is the bit that correlates with this, but it doesn't, you can't explain it with this simple formula. You know, so I've got phi naught of flux per Skirmion and calculate. And you know, you're orders of magnitude away from what we're actually seeing in this experiment. Okay,
something to think about. Okay, any further questions from anybody? I think I'd like to thank the 90-something, 95 or so of you that were watching today. That's very nice. And then let me, here it will be here. I'm gonna go to the end streaming here. Okay, and that.